Hi everyone, my name is Divya and this is my project, The Effects of Aerobraking on Time and Variable Altitude. So now the word aerobraking might seem to sound like some fancy jargon that you've never ever heard before. But if we break down the word really quickly, we can think of aero talking about the air or the atmosphere and braking just like how we brake in a car. So a spacecraft uses both of those words, I guess, into one to aerobraking. So what happens is a lot of the times it's a lot of fuel and cost and a lot of time to take a spacecraft to transfer its orbit, which means to go from one orbit to another. And so we use aerobraking to basically use a planet's atmosphere in order to slow down a spacecraft instead of just using fuel. And this allows for the spacecraft to carry less fuel and carry more payload or more things on the craft. Additionally, this is a little bit of a diagram of what it looks like. So for example, we have the spacecraft going into orbit. Jettison just means that the payload is being released. And then once it's closest to the atmosphere of the planet, it dissipates energy, meaning that the drag or the slowness of the atmosphere is helping the spacecraft to slow down. And here's a larger view of that same process into multiple stages. And so this applications can be used in the first human Earth and Mars mission in 2035, in other planets such as Uranus, Neptune, and as seen in the early 2000s, which used aerobraking in the Odyssey mission. So, my main project focused on a couple of key questions. How does altitude affect the time taken for a spacecraft? Will it speed up or slow down the spacecraft? And how does aerobraking reduce travel time and cost efficiency? So, the first part of my project is very mathematics heavy. So, this might seem a bit confusing and a bit daunting, but let me break this down for you. So we can think of dE over dt as the change in energy over the change in time. And so with this change in energy versus change in time, we can find our R dot. And we can think of R as basically the radius of a planet plus the altitude of a spacecraft. For example, if I was on Mars and I was 500 kilometers above the Martian atmosphere, it would be from the center of the planet all the way up to those 500 kilometers. And so here are some other important variables. Mu, that's a constant that varies on Earth, Mars, and any planet that you look for. And then rho would be our density and E our energy. So in order to just validate that this equation that I derived would work, I plugged in my own values. For example, density, mass, a set altitude, so just one altitude, the mu constant of Earth, and many other variables. And using this, I was able to find the change in R. So that means the change in how low a spacecraft would be going in meters per second, and plug it into the second equation, which allows us to find the time it takes. So that's what we're extracting here, just subtracting the R initial value from the R final value and dividing by the R dot, which we found in equation number 3, which gets us with these variables 255 days to complete the aerobraking maneuver. So after I validated that this equation did work, I used a simple Python script in order to model what it would look like if a spacecraft actually descended from 150 to from 400 to 150 kilometers. So what I essentially did is using the equation, this section here from negative 1.02 all the way till the altitude allows us to account for variable altitude. As before here, we only have one singular altitude at 275 kilometers. Now we have to account for all altitudes between 150 to 400. And so we then add the result to the R value, which constantly keeps on updating. And to find the altitude, we just subtract the radius. In this case, the radius of Earth is 6378. And then we just append these values while the while loop is running into a array, which will then be plotted. And for each iteration of the while loop, time is added by 1, and so that would be our time in seconds, essentially. So now our results. As we see over here, this is essentially what I predicted from the beginning. We see at the beginning the spacecraft is descending and time decreases at a pretty shallow, almost linear rate, you could say. And then, as we have the spacecraft decreasing even more, the time exponentially decreases, showing that as the spacecraft gets lower and comes into more contact with the atmosphere, in this case, Earth's atmosphere, we see the time drastically decrease. And so, again, this is due to the atmospheric drag and friction, and indicates that the lower the spacecraft travels, the faster its decrease in altitude, and the less time it would take for that spacecraft to go to a planet, for example. So now, with the overall study, my conclusions were this could be beneficial to many space missions and applications. As I said before, the first human Mars mission would really use aerobraking in order to save so much fuel, so much time, and so much cost. Because as we've seen, for example, I was talking about the Odyssey mission, that could take billions of dollars. And so, just these small things, such as aerobraking, could make a huge difference for the success of the mission. And it's also important to note that just using aerobraking alone would take too much time. For example, in the Odyssey mission to Mars, it took around 70 days. So, in many practical situations, it would be more useful to use a combination of fuel as well as a combination of aerobraking in order to achieve the most efficient results. And then again, these parameters for the study were modeled specifically off of Earth. However, in future studies that I also plan to conduct, this same equation and this same process can be translated to, for example, Martian data using Martian mu constants, using variable densities on Mars, as well as variable altitudes. And so this could be very helpful, especially when it comes to this. And so I would like to give a special thank you to both of my mentors, Dr. George and John. They helped me throughout the whole project, and not only was I able to interact with them with my project, they were able to give me some guidance into what I want to do in the future. I want to personally be an aerospace engineer, and they helped me go through what they do in their own college and the work that they do, as well as how this specific research can be applied to many different things. And additionally, Talaria, thank you so much for helping me connect with my mentors. I was able to enter this amazing community of such positivity and like minded people